Okay, so my name is Tomáš Pluskal, and I'm from the ISMB Prague, and this is the last talk of this cozy, so bear with me, you can go home soon. Okay? But I would like to tell you something about the last generation of the MZmine platform. This is a mass spectrometry community, so I suppose you have at least heard about MZmine before, so I'm not going to introduce too much the software. I would rather like to focus on what's new. This is just a brief summary of the history and the community behind it. So the MZmine platform was actually, the development was started in 2004, and the first paper was published in 2006. And then since then, there has been a continuous development. You can see the number of lines of codes increasing over time. And the second generation MZmine 2 here, but still continued development, actually accelerating in the last 5-6 years as the community has expanded. And last year, we released the third generation MZmine 3. And this is an effort of quite a large community of contributors. So you can see here more than 53 contributors, many of them with large contributions to the code. And the software is quite popular in the metabolomics community and lipidomics community. So lots of downloads, lots of citations to the papers, and so on. Okay, so one thing that we identified as a major bottleneck in the previous generation was actually performance on large data sets. So we put quite a lot of effort to optimize all the internal algorithms and the data storage within MZmine so that we could accommodate large studies and larger sample sizes, because with the new technologies such as ion mobility separation, also the files themselves are getting bigger and bigger. So it's not uncommon now to process tens or hundreds of gigabytes of data at once. And so here you can see a little chart, how much faster is MZmine 3 compared to MZmine 2. But also in the paper, we demonstrate how we can process large data sets of hundreds to thousands of samples. We actually show 8,000 samples processed on a regular PC in a couple of 40 minutes. Okay. So the performance has increased significantly. This is not the only new thing in MZmine 3. So another thing where we put a lot of emphasis is the development of molecular networking tools and integration with molecular networking platforms such as GNPS. And what comes hand in hand with these other improvements is the support for various modalities of mass spectrometry data. So nowadays, people use ion mobility separation, they use imaging mass spectrometry, and all these data come with their characteristics. And now in MZmine 3, you can actually load and process all the data together. And with this comes some complexity of the data processing process, and because the data types are different, they also require different approaches to data processing, and then setting up the data processing pipeline actually becomes quite complicated. So for that, we have introduced an MZ wizard, which allows you to, in a relatively easy way, configure your data processing pipeline. So I will introduce this a bit more in detail. But before I go to that, I have to say the major new feature in MZmine 3 is the dark mode, as you can see here. And obviously, the whole user interface has been completely rewritten and redesigned. It's much more smooth, and it's skinnable, and it's more responsive. It's very nice. But I'm just going to leave this there for a few more seconds so you can appreciate how cool it looks. Okay. This, by the way, is an option. You don't have to use the dark mode. So I talked about the different modalities of mass spec data. So this is just an example of a couple of different instruments that use different technologies to separate, introduce the sample into the mass analyzer, and measure the masses and potentially fragment the molecules and so on. And all these come with their own specific of how the data looks like. So if we look at LC-MS data, we have some spectra where we can take a single ion and we can look at the ion over retention time. We can build extracted chromatograms. Within these chromatograms, we can detect some features that we use to represent the metabolites. Okay? On the other hand, in imaging data, we also have spectra. The spectra might be a bit more complex because there is no chromatographic separation. And we don't have the time dimension. There is no chromatography, so we don't have retention time. We don't have any features. but instead we have the spatial dimension, we have coordinates, and we have images. We can make extracted images for each of these masses. It's a totally different way how to look at the data. So what the MZ wizard allows you to do is to select what type of sampling or introduction of the sample are you using, what type of instrument, the mass analyzer you're using, and what is the purpose of your experiment, whether you're doing untargeted metabolomics or you're doing targeted measurements or library building and so on. And then it builds the data processing pipeline for you, and it fills in all the parameter values with some default values based on what you selected here. And this is how it looks like in practice. You just go to the menu processing wizard, and then you select what type of separation or sample introduction you're using. If you're using ion mobility, then you can select what type of ion mobility separation you're using. You select the mass analyzer and the purpose of your experiment, and you just click on create batch, and then the software creates a batch of processing steps, including the parameter values, which you can, of course, then modify and optimize if you want to. This is how the batch created by the MZ wizard looks like. And this represents all the main processing steps that a typical untargeted metabolomics experiments would require, which are illustrated here. And these images, by the way, are copy-pasted from Nature Protocols article that's currently under review. So hopefully in the near future, you will see all these workflows also published in a nice, easy to access protocols article. Okay. So now I would like to focus a little bit more in detail on LCMS with ion mobility separation, because that's one of the new things. So this looks familiar. This is spectrum, right? And this is a chromatogram. But if we add the ion mobility dimension to it, then we actually call this a frame, because these different ions here might have different mobility value. And if we're looking at the spectrum as a whole, just ignoring the mobility, and we call this the frame. Okay? And this is a chromatogram, so retention time over intensity, and we see some different ions here, which might be isomers, so they might actually overlap in the chromatographic separation. Now, if we expand this frame into the mobility dimension, we get something that's called the frame heat map. So now we see mass over the mobility and the intensity represented by color here. So we see those three different ions now separated. And if we take this chromatogram and we expand it into the mobility dimension, we get ion mobility trace. So again, we now see three separated ions in the retention time across the mobility. So there are different ways how to look at this data because it's four-dimensional. Okay? So in MZmine 3, you can now open this basic module that we call IMS raw data overview, which allows you to see the data with all these views. Right? So the first view is the chromatogram. So you have retention time over signal intensity, and you can configure the chromatogram so you can see some extracted masses and so on. You can play with it. Now you can see the spectrum, which in this case is the frame. So at the selected time in the chromatogram, we see the frame here. And we also see the expanded version of the frame heat map. And on the side, we see a mobilogram, which is simply a sum of all the signals across the mobility dimension. Now we also see the expanded version of the chromatogram, so the ion mobility trace here. And when you select a particular point in the ion mobility trace, you also see the individual mobility spectrum. So the sum of the mobility spectra is this frame. Okay, so it's a pretty complex view, but you can actually zoom with this, you can move with this, so it's all interactive, and you can see your data in all its complexity. Now, next step is the processing of ion mobility data. So this is the basic feature detection pipeline in MZmine. We start by some algorithm called mass detection, where we find the individual ions in each spectrum. We remove the noise, the trace signals, and we build chromatograms for all the ions, and then we identify individual features within those chromatograms. And those features are then aligned across samples. If you're using ion mobility separation, then you have to add some additional steps here. So you have to take each of your features that were detected, and expand them into the mobility dimension. And if you have multiple peaks in the mobility dimension, then you have to do another round of resolving where you separate them into individual features in the mobility dimension. And this is then followed by additional modules for annotation, such as ion identity networking, molecular networking, other external annotation tools and statistics and so on. This is not different from regular LCMS. And this is how the results look in MZmine, where you have the feature table, you can see the chromatographic shape, you can see all the values regarding that feature, the peak area, the height, retention time, charge, and so on, the identity of the ions, and so on. Okay, so this was about LCMS. Now let's switch gears and let's take a look at the imaging data with ion mobility. So again, in MZmine, you can load your imaging data and you can view it. So all these plots are interactive. You can zoom, you can select masses, you can play with it. You can click in any point and you see the spectra at that spatial coordinate. So this is just a way to view the data. And then again, if you want to process the data, now we are not detecting features anymore, but we are detecting extracted images. So again, we start with the same mass detection. But then we have a module called Image Builder, which builds an extracted ion image for each mass that was found in the data. And then if you're using ion mobility, then you have to expand these images into the mobility dimension and separate them by a resolving module to get extracted images for each of the potential isomers that might have the same mass. And that's then followed by additional modules such as isotope removal, isotope filtering, and this can be also then aligned to your LCMS datasets, which I will show a bit more in detail later. So this is how it looks in practice. So in MZmine, if you run the image builder on your data, on your imaging data, you get these cute images for all your ions that you detected. And then when you expand them into the mobility dimension, for each image, you get the mobilogram. So you see the signals in the mobility dimension. And you can see in this case, for this mass, we have actually two peaks in the mobilogram. So these have the same mass. They are kind of merged in this image. So then we use the resolving module to separate them. And we get two different extracted images in the feature table. So you see a different spatial distribution for these two isomers. And this is how the final feature table looks like. So you can see it's similar to the LCMS data. You have all these values here, but then now we really have images, we have spatial distribution. And I mentioned that we can now align these data sets together. So why would you want to do that? So if you're using MultiMS, you're doing imaging, it's probably because you care about the spatial distribution of your molecules. So that's important for the biological context that you're studying. But in MultiMS, it's very difficult to obtain MSMS data. You typically have to do it manually, and it takes a lot of effort. You cannot do it in high throughput. So you have very limited information how to annotate your signals. So you only have the accurate mass, and in some cases, you can have the MSMS spectra collected manually. In contrast, in LCMS, you typically can do data-dependent acquisition or data-independent acquisition. So you have lots of MSMS spectra, which you can use to annotate your signal. So you have not only the mass, but also the retention time from the chromatography, lots of MSMS spectra. You can compare this to internal standards and so on. So we would like to combine the advantages of these two approaches by aligning the data sets. And so in the MZmine 3 paper, we demonstrated this on brain tissue data. So here we take Stefan's brain and we analyze it, the same tissue by LCMS and also by multi-imaging. And in this case, we did on a Bruker-Timstorff, so you can actually load directly the Bruker-Timstorff data into MZmine. For other instruments, you have to use the open formats like MZML, IMZML. And we do this data processing that I showed. So we do the feature detection of the LCMS data and the image detection with the ion mobility resolving on the imaging data. So we have these two feature lists. And then we use the aligning module, which combines the data based on the accurate mass measurements and the mobility measurements. So in the imaging data, you don't have retention time, but you have the two values for each feature, the accurate mass and the mobility. And those two are enough to say with reasonable confidence that it's the same compound. So we can align them together. So now in the feature list, we have the mass, the mobility value, we have the mobilogram, and the extracted ion image. And this is the chromatogram. So it's all in one row. And what then that allows you to do is, for example, run the lipid annotation module in MZmine, because this was a lipidomics experiment, which gives you lipid annotations based on the MS spectra that you collected in your LCMS experiment, but you can now bind these annotations to your spatial distribution of the individual isomers separated by an ion mobility in the imaging data. Okay. Now, one more example. This is a study of mouse spleen data produced by Patrick Helmer in Münster. And here, again, the mobility value serves as an additional identifier on top of the accurate mass. Okay? And you can use it together with the mass to correlate data that might have different retention times. And in this particular case, what they did is they used two different chromatographic systems. So here you can see two different peaks in the chromatogram that belong to the same molecule, and it's because one is coming from helichromatography and the other one is coming from reverse phase chromatography. And using the mass and the mobility value, you can align these together, and that helps you increase your coverage in your, if you're, for example, interested in lipids, so increasing the coverage of the different lipid classes. So here we have the mobilogram, and the mobility values are the same, so we can use that to align the data sets. Now, if we add imaging data into this mix, so we get the spatial distribution of all these masses. Again, we have ion mobility enabled imaging, so we have mobilograms for all these extracted images, and we can align it all together. So now we have this complex feature table where we have the helic data here, the reverse phase chromatography data here, and the imaging spatial distribution here. And we can be fairly confident that on one row we have a single molecule in all these systems. And now in the last part of my talk, I want to talk more about annotation, and specifically spectral libraries. So you have probably seen some diagrams like this in metabolomics, which summarize the level of confidence that you can have in your annotations, starting from the lowest confidence where you only know the exact mass, and going up to high confidence where you have confirmed your compounds with the reference standards. In MZmine, we have a number of modules for annotation. So you can start with ion identity networking, which helps you identify the ion types and cluster your ions into families that are coming from the same actual molecule in the mass spec. Chemical formula predictions to identify the chemical formulas, local database search or spectral library matching to identify the structures. And you can also do other things like molecular networking or external tools like Sirius for predicting the structures and compound classes and so on. So all these tools are there, and that's nice. When you combine that with the molecular networking, it helps you propagate your annotations to additional features. So you might identify some, but you know based on the structural similarity from the molecular networking that these others would be similar, and you might identify how similar and what are the differences. So this is all nice, but even with these approaches, in the study of natural products, especially from plants, we still see very low annotation rates of less than 20%. Okay? And we think it's time to really put some effort into improving spectral libraries. Okay? So why should we care about spectral libraries? I know this sounds a bit boring. It's like 1990s, spectral libraries. There's nothing really too exciting. But besides the fact that we use spectral libraries for direct spectrum matching, so we can do this in MZmine also. You take your spectra, you match it against a library that you download or you create. The spectral libraries are actually also used to train all these fancy new machine learning based methods, like CSI finger ID, CFM ID, MS2 query, MIST, and so on. So these are very smart approaches, but they also rely on the spectral libraries that we have for training. And what I would like to argue here is that the spectral libraries that we have are actually extremely limited. So this is a list of the spectral libraries that are available now, both the open and free ones and the commercial not so free ones or not so accessible ones. And if we take the biggest open library, which is I think the GNPS library, it contains, let's say, about 20,000 unique compounds and a couple of 100,000 of unique spectra. And that's really not that much. If you think about how many molecules are out there in nature, 20,000 is really not that much. The commercial libraries, they typically contain more spectra, but not necessarily more compounds. Okay, so these are very small numbers. So I would like to tell you a story that's called 15,000 compounds in 10 days, or automatic generation of an open MSN library. This is a story from my lab. So we started with 15,000 compounds, and 10,000 came from the MedChem Express library, which is a library of bioactive molecules. It contains anything that's bioactive, including drugs. And the second library was a library of 5,000 natural products that we obtained through a collaboration with NIH. And our goal is to produce a really comprehensive library on this, not only covering fragmentation MS2 spectra, but also covering different collision energies and different precursors for MSN characterization. So we not only collect the MS2, but also MS3 on the different peaks found in MS2 and MS4 and so on up to MS5. Okay. So we're basically trying to obtain this complex, comprehensive spectral tree with full characterization of each molecule. Now you can imagine to get all this information on the mass spec, it takes some time. So we found that to collect one full tree on one molecule takes about 13 seconds. Yeah? That's not compatible with the typical LCMS experiment where the peak might just last a couple of seconds. Yeah? So instead of using LCMS, we switch to flow injection, where we just inject the compound into the flow from the LC without any separation column, and we get this broad peak. But 40 seconds was still not enough for us because the compounds typically come in mixtures, like 10 different compounds per injection. So we need actually more time. So then we switch to yet more fancy setup where we have two pumps. One delivers the sample in a very slow flow rate, and the other one delivers the flow from the LC. And then they're combined, and that gives us this nice broad peak for about 90 seconds, which is enough to collect all the spectra that we want. And then we combine this, so the samples are injected directly from plates, collected on an Orbitrap IDX instrument. And then we have the metadata because we know what compounds are in the library. So we have some sort of table of compounds, which then needs to be cleaned up because we found the representation of the compounds is sometimes different. Sometimes they are represented as salts and so on. So we have to clean this up a little bit. And this is all loaded into MZmine. And then MZmine takes care of the library building and annotating the spectra and then exporting it into some format that's compatible with library search. Now, how does this library building works? So we use, again, the same modules that I showed before for detecting the ions. Then we perform the feature detection, and then we use the local database search module to annotate all the features that we found. And we perform some quality checks on the library. The feature detection module, it includes the standard feature detection algorithm that I showed before, including the ion mobility resolving if it's done with ion mobility. But it also includes the MSN3 builder, which is a new module that puts all the MSN spectra together into this tree form. So we get a complete structural characterization of that molecule in the feature list with the feature. This is how it looks like after you run it. So you get, again, a feature list with all the values about the feature, the chromatographic shape, which in this case is just a 90-second long blob, and the annotation from the library search module. And I mentioned the data quality checks that we perform. So we first check whether the spectrum might be chimeric. So we look at the isolation window in the MS1 scan, and we see if there is any contamination. If there is a tiny bit of contamination, we would still consider it clean, but if there is some significant contamination, then we say the MS spectrum would be chimeric and we would discard it. And then we also look at the quality of the MS or the MSN spectra by looking at the chemical formula of the precursor, which we know. And then we try to explain all the fragments or the old neutral losses with chemical formulas that must be a sub-formula of this parental chemical formula, because we know that the part that was lost must be a subset of the original molecule. And then we calculate how much of the signals, how much of the intensity can be explained this way. And if it's below certain threshold, then we say the spectrum is just weird and we also don't use it. Next step that we perform is spectrum merging. So we take all the spectra at 1 ms level, different collision energies, we merge them together, and then we also merge all the spectra from the different ms levels to create one metaspectrum that is not a real experimental spectrum, but it actually is the richest information about that one molecule that can be useful exactly for training algorithms such as CSI finger ID. Because actually what they do is they also merge all the signals that they have from different collision energies and so on. So this is just one representation of that molecule. And this is how it went in practice for the MCE library. The library came in plates, and each plate had 10 compounds in a well. So it was 3 plates in total. It only took 3 days to analyze on the mass spec with this method, because we are not using chromatography, so it's very fast. And we collected over 400,000 spectra. Now, of these, many, like 7,000 unique compounds could be matched to the annotated table of that library. And that's because there were actually the same compounds represented as different salts. So then we have a little bit less than 10,000 compounds in there. Out of those 400,000 spectra, only 3 were identified as chimeric, so it is also a pretty nice result. And then we use this library building workflow on that. We check the quality of the spectra, and here you can see that the vast majority of the spectra actually was perfect, and then overall the quality was acceptable, I would say. So this approach works for producing libraries in high throughput. And then what we tried is to take this data and try to annotate the spectra by matching them to the biggest available open spectral library, which is the GMPS library. That contains about 20,000 compounds, about 600,000 spectra. And what was quite surprising was that we could only get 14% annotation rate. So these are pretty well known molecules. They're coming from a commercially available library of bioactive molecules. They're not super unique, they're not super weird, but we still got only 14% annotation rate. So I think this really shows how bad is the situation with the available spectral libraries. Okay? If you take a look in more detail, some parts of this molecular network, for example, here we have the beta blockers, which are fairly well covered in the GMPS library. Here we have sartans, which are less well covered, and here we have cephalosporins, where we couldn't find a single match. So we really think it's time to do something about this, and we started this effort, but we also think that we should not be the only ones, and we're trying to find more collaborators. So basically anyone who has a mass spec and who has compounds and who is willing to help. Now we already have a network of collaborators who are willing to join this effort and collect some data. And the goal would be to collect GCMS spectra and retention indices on volatile compounds and on non-volatile compounds, use chromatography, ion mobility to get all these additional values, and also the MSN approach that I showed here to get the full fragmentation tree. So essentially get as much data as possible. And why this should be useful? Well, I hope it would increase the annotation rates in untargeted metabolomic experiments. It would definitely help for training the computational tools such as Sirius, MSLibquery, and so on. But also the fragmentation trees could be helpful for making predictions on substructures in your experiments and so on, because currently there is no open database that contains MSN spectra. There's only MZcloud, but that's not really accessible. And I showed that within 3 days, we collected data on 10,000 molecules, right? And if we look at GMPS, it has 20,000 molecules at the moment. So essentially within a few days, we could increase this library like 50% more. So I think that shows that this can be done. So this is an open call to everyone. If you happen to have access to chemical collections, small or large. We would love to include them in our data collection. So please share your compounds. Only a tiny amount of substance is needed. Mixtures are okay. We can do the pipetting and dilutions ourselves using robots, and all the data will be published, of course. And finally, I just want to say that if you're interested about in MZmine and you want to find more information, we have a website. We have extensive documentation for the data processing. We're very active on Twitter, which I guess now I have to change this logo. And there we also publish announcements about occasional group Zoom calls with the users, so anybody can join and discuss with the developers what they're struggling with. We have lots of videos on YouTube where we have tutorials how to use the software. And if you'd like to join the development, this is the GitHub. You are most welcome to come and join us. And you can also report issues if you find some problem or bug in the software. Now, as I mentioned, the processing is becoming more complex. So we also try to organize hands-on workshops where we train people how to use MZmine. A couple of these have already been done and are quite successful. The next one is going to be next month in Copenhagen, and then in October in Munich. And next year we're planning two, one in Prague and one in Japan. This is from the last workshop in Prague. And with this, I have to thank all the collaborators and all the people who are behind this effort, mainly Robin, who is the chief developer of MZmine 3, and Stefan, who developed all the modules for ion mobility and imaging, and Corina, who is behind this effort of building spectral libraries. And so we received a big grant from the Czech Science Foundation, but also support from Google Summer of Code and EPILIPIDNet. And these are the logos of the institutions where we received some code contributions to the software from. Okay. And I'll be happy to answer any questions. Thank you.
Thank you, Tomáš. When you first showed the increase in the number of lines of code, I was also maybe thinking that maybe you just became worse programmers over the years, but then showing all the amazing functionality, I think that was pretty convincing. All right, any questions from the room?
Hi, Thomas. Very interesting, especially the part of the database, because this is something that we also faced quite often. And we also realized that the number of the spectra, limited number of spectra that you were mentioning for the public repositories, actually only report protonated and deprotonated species. And therefore, there is also an effort. You were talking about collecting information on the fragmentation, different MSMS levels, and so on. But to me, it would be very important also to increase the number of adducts, because with the adducts, otherwise we have a lot of unknown that actually are the same molecule, and we can increase their notation. What do you think about?
Yeah, that's a great point, and I did not specifically mention that, but we can use this ion identity networking to annotate the adducts directly in the data that comes from the data collection of the library. So all these different adducts will be included. Yes.
When creating this merged spectrum and searching it against GMPS, might that not also be driving some of the spectrum match scores down, because that is not a representation in which you would get like an experimental spectrum or another spectrum that is not undergone this merging process. So if you then have additional peaks, that drives your cosine similarity down if they're not in like a single collision energy or fragmentation spectrum.
That is true. Yeah, I think if we have a database of these metaspectra, let's say, then maybe we need to adjust the search algorithm. So we cannot use just the plain cosine similarity, but maybe use something that's aware of the fact that we are working with these metaspectra. But I still think this is a rich representation, right? Because different instruments gonna produce slightly different fragments. If we include all the possible fragments in that spectrum, we have the highest chance that we match something. And the same goes for the computational methods like CSI finger ID.
I was trying to check your manual, but then I just ask you. Does it also run in Linux with command line?
Yes.
Okay, thank you. Almost there.
And continuing in that vein, can you also run it in an HPC environment? And how does it scale as you throw more cores, more memory, etc. at it?
So many of the algorithms in MZmine are multi-threaded. So the more cores you have, the faster it's going to work. It's not really like a multi-computer system that you could take advantage of a meta cluster and distribute your computation to many nodes. That's not something we do, because the origin of MZmine is to be an interactive software where you actually see your data, right? So this is not really like you can run it on a cluster, but you're not going to get much advantage out of it, I would say.
Thanks, impressive work. I have a question more on the meta level. I'm wondering, like, what's your experience to keep such a community going over such a long time with so many involved players? I mean, many projects of that size fail at a certain point in time. Do you have a secret recipe to share?
Secret recipe.
Or not so secret one?
Yeah, I mean, I always try to be welcoming. You know, oftentimes people approach me and say like, hey, could you implement this feature in the software? I'm like, no, but you can implement it and I'll help you. And that's how the community grows. And at some point, yeah, of course, it's getting big. So we need to have a little bit of governance of what's going to be included, what's not going to be included. But so far, it hasn't reached unmanageable levels. So that's just my experience. And it's been almost 20 years, so it's been quite some time.